Hello, my name is Kirti. In this lecture, we shall try to understand a very important topic from colloidal chemistry, that is electrical double layer. So, if you had appeared for the CSIR NET June 2024 exam, which was held in the month of August, then you might know that there was a question based on DLBO theory in the exam, okay? So the question was pretty much straightforward. If you know this theory, it will take only half a second for you to answer the question. But to know this DLBO theory, you need to have a prior knowledge of what is electrical double layer. So in this class, we shall try to understand electrical double layer, and in the upcoming class, we will discuss DLBO theory. Okay. And this electrical double layer itself is very important for CSIR NET. So questions can be asked from this topic also. Okay. So we will start the lecture by brushing up the basic concepts of colloidal chemistry that will help us to understand electrical double layer. So we will see only that is required, okay? We will not see the entire colloidal chemistry, we will see only those topics that can equip us to understand this EDL, okay? So first we will start with what are colloidal solutions. Colloidal solutions, then we will see what are lyophilic colloids. Lyophilic colloids, and then we will see what are lyophobic colloids. Lyophobic colloids, and I think this is sufficient for us to understand electrical double layer. Okay, so let us begin with what are colloidal solutions. Okay, rather than colloidal solutions, let us begin with what are solutions. So in chemistry, what are solutions? The solution is a mixture of two or more components. For example, if I take a beaker, this is a beaker. If I take a beaker with water in it, and if I add a tablespoon of salt, NaCl, rock salt, okay? If I add salt in it, then what happens? It becomes a solution, right? A mixture of salt and water is a solution. Here the substance that is taken in small quantity, less quantity, is referred to as solute. So in this case, sodium chloride is the solute, and the substance that is taken in large quantity is referred to as solvent. So in this case, water is the solvent. So solution is a homogeneous. Okay, let me not use the term homogeneous. I'll tell you why I am not using homogeneous. Just define solution as a mixture of two or more components. Here we have two components, sodium chloride and water. So here sodium chloride is the salt solute because it is taken in less quantity, and water is the solvent because it is taken in large quantity. But when we discuss colloidal solutions, we do not use this term solute and solvent, but instead we use something called dispersed phase and dispersion medium. Dispersion medium. So what is this dispersed phase? So something that you are distributing or dispersing or diffusing in a medium is dispersed phase. So in this case, if this had been a colloidal solution, it's not a colloidal solution, but if this had been a colloidal solution, NaCl would be your dispersed phase. And what is dispersion medium? The substance in which you are dispersing your dispersed phase is the dispersion medium. So if this had been a colloidal solution, the water would have been dispersion medium. But this is not a colloidal solution. I am just giving you an example. So the solute is analogous to dispersed phase and solvent is analogous to dispersion medium. And while I discuss this colloidal solutions, I will always use these terms dispersed phase and dispersion medium instead of solute and solvent. Okay. And it takes me a lot of time to write dispersed phase and dispersion medium every time. So we will give it a short form, that is DP, dispersed phase, and dispersion medium would be DM. Okay. time when I want to say dispersed phase, I will write it as dP and dispersion medium as dF. Okay, so now we know that solution is a mixture of two or more components. Here is an example, NaCl in water. It is a binary solution because it has only two components, that is salt and water. If it has three components, it will become a ternary solution. But for examples, we will consider only binary solution. So now we know solution is a mixture of two or more components. So the solution is divided into three types, okay? The solutions are divided into three types. On what basis? So on the basis of the size of solute particles or on the basis of the size of dispersed phase particles. So based on size of dispersed phase, solutions are classified into three types. So first one is the true solutions. Second one is the colloidal solutions. So this is of our interest, colloidal solutions. And third one is the suspensions. Suspensions. Okay, what are true solutions? So the solutions in which the dispersed phase particles are very less. I mean very small in size, that is less than 1 nanometer. Not less but small in size. If the dispersed phase particles, which are nothing but solute particles, if the size of dispersed phase particle is less than 1 nanometer, then it becomes a true solution. So what is an example of true solution? It is the same that we had discussed earlier, salt in NaCl in water. When you dissolve this NaCl in water, the size of one NaCl is so small and it will obviously dissociate into Na plus and Cl minus in water. So size of one particle is very very small, that it is less than 1 nanometer, that you can't even see this particle with the help of a microscope. And what are suspensions? So in suspensions the particle size is very huge, it is greater than 1000 nanometers. So what is the best example of suspension? You can collect some water from any dirty lake and pond and put it in your glass beaker. Then you will notice that there are small dust particles in the water. Okay, so that kind of solution comes under the example of suspension. So what is the example of suspension? Muddy water. So these particles in suspension, the particles of suspensions can be seen with the naked eye. Okay. In true solutions, you can't even see with the help of microscope, and in suspensions, just you can easily see with your eyes. Okay. And if you leave this suspension as it is still for a long time, what will happen? All the mud particles will settle at the bottom. Okay. So those are suspensions. And what are colloidal solutions? So if the particle size ranges from 1 to 1000 nanometer, or if the dispersed phase particle size ranges from 1 to 1000 nanometer, such solutions are called colloidal solutions. So what is the best example of colloidal solution? Some protein in water. So we know that proteins are long chains of amino acids. So they are very large. They are typically in the order of 5 to 10 nanometers. So this is just typical size. Not every protein falls in this range. Sometimes they fall below 5 or sometimes they also exceed 10. But typically protein size is from 5 to 10 nanometers. So one protein molecule will have size between 5 to 10 nanometers, and this size falls in the range of a colloidal particle size. So this protein solution is the best example of a colloidal solution. And what could be one more example? Okay, you consider this gold salt. So gold is metal gold. Its Latin name is aurum. So Au is gold, aurum. So gold salt is also an example of a colloidal solution. Now you can ask me, how gold sol becomes a colloidal solution? Because we know that gold atoms are very small in size. The size of gold atom is somewhere between 0.14 nanometers to 0.15. Okay. So when the size of gold atom is less than 1 nanometer, how can it form a colloidal solution? So that should be a question. So what happens? Gold in colloidal solution does not exist as individual atom, but so many number of gold atoms, they aggregate to form a particle. Large number of gold atoms, they aggregate to form a particle whose size ranges between 1 to 1000 nanometer. Therefore, gold can form a colloidal solution. It's not the individual atom but the aggregate of so many atoms to form a particle whose size ranges from 1 to 1000 nanometers. So gold sol can be possible by the aggregation of gold atoms. Okay, now our interest is this colloidal solutions, because this is only required to understand electrical double layer. So we do not need true solutions or suspensions. Okay. Now let us look at classification of colloidal solutions. Colloidal solutions. So these colloidal solutions, they have three classifications. 1, 2, 3. So the first classification is based on what? Okay, the first classification is based on the physical state of dispersed phase and dispersion medium. So the first classification is based on physical state of dispersed phase and dispersion medium. By physical state, what I mean? I mean whether dispersed phase is solid, liquid or gas, or dispersion medium is solid, liquid or gas. For example, if your dispersed phase is gas and dispersion medium is liquid, then the colloidal solution is called aerosol. Aerosol. And suppose your dispersed phase is liquid and dispersion medium is also liquid, then such colloidal solutions are called emulsions. So there are so many combinations like dispersed phase solid, dispersion medium liquid. Okay, and suppose let us take one more example. Dispersed phase is solid, dispersion medium is liquid, then they are called salts. Okay. So we don't require this classification. If you want to refer this classification, you can look for this classification in NCERT or Telugu Academy textbooks. Okay. So we don't require this for now to understand electrical double layer. So I'll skip this. And the second classification is based on the interaction between dispersed phase and dispersion medium. And the third classification is based on the type of dispersed phase particles. The type of dispersed phase particles. What do I mean by type of dispersed phase particles? We have just seen that in protein colloidal solution, the colloidal solution in which the particle is protein, here the single particle has the size in the colloidal particle range. Okay, one protein molecule has a size from 1 to 10 nanometers, right? So one protein molecule is a colloidal particle here. Such colloidal particles are called macromolecular colloids. Macro means big molecule, macromolecular colloids. But in the case of gold sol, gold colloidal solution, What did we see? We saw that so many gold atoms, they aggregate to form a particle which is in the size, whose size ranges between 1 to 1000 nanometers, right? This kind of colloidal solutions have some name. They are called macromolecular colloids, and the other are multimolecular colloids, I guess. Multimolecular colloids. Because multiple number of atoms are aggregating to form a particle whose size is in the colloidal range. Okay. So therefore such colloidal solutions are called multimolecular colloids. I'm not sure about this name. If this name is wrong, I'll give the right name on the screen. Okay. So based on the type of dispersed phase particles, if the one particle size ranges in the colloidal particle range, then such colloidal solutions are called macromolecular colloids. Example is protein solution. And if large number of atoms, they aggregate to form a colloidal particle, such solutions are called multimolecular colloidal solutions. But we do not need even this classification. What we need is this classification: interaction between dispersed phase and dispersion medium. So we are not going to pay attention to these two things. Okay. So based on the interaction between dispersed phase and dispersion medium, colloidal solutions are classified into two types. They are lyophilic colloids and lyophobic colloids. Lyophobic. So what are lyophilic colloids? So lyophilic colloids are those colloids in which there are attractive interactions between dispersed phase and dispersion medium. Okay. Attractive interactions. That means dispersed phase is affectionate towards dispersed medium and it does not mind dissolving into the dispersion medium. Such colloids are called lyophilic colloids. They don't have problem with the dispersion medium or the solvent. Okay. They are affectionate towards the solvent and they dissolve easily in the solvent or dispersion medium. But in case of lyophobic colloids, we know that this phobia stands for fear, right? So in case of lyophobic colloids, the colloidal particles, they have some kind of fear towards the solvent. They do not like to dissolve or disperse into the dispersion medium. So such colloids are called lyophobic colloids. So they are solvent fearing colloids. Okay. Solvent fearing colloids. So lyophilic colloids are those colloids in which the colloidal particles easily disperse into the solvent because they have attractive interactions, and lyophobic colloids are those colloids in which the colloidal particles do not like to disperse into the solvent, right? So if lyophobic, what do I say? Okay. If the colloidal particles, they easily disperse into the dispersion medium, then the colloidal solution must be stable, right? So lyophilic colloids are always stable. But when I speak about lyophobic colloids, I already told you they have some kind of fear towards the dispersion medium. They do not like to dissolve into the dispersion medium. Therefore, they are not stable, right? So colloids are stable only when the colloidal particles are dispersed throughout the dispersion medium. But since in lyophobic colloids, the colloidal particles do not like to disperse into the solvent, they settle down at the bottom. Therefore, lyophobic colloids are not stable. Okay. So if you want to prepare lyophilic colloids, how do you do that? You take the colloidal particle of which you want to prepare the colloidal solution. You just disperse into a suitable medium. So you just disperse colloidal particles into the suitable medium and lyophilic colloid is formed and it will stay. It will not aggregate or it will not destabilize itself. It will just stay like that. Okay. Since the particles have attractive interactions towards the solvent, so the particle is surrounded by the solvent medium, and likewise each particle has solvent around it, and this attractive interactions keep this lyophilic colloid stable. But lyophobic colloids are not stable because they do not have affinity towards the solvent. Okay. So since lyophobic colloids are not stable, it is not easy to prepare lyophobic colloids. But lyophilic colloids can be easily prepared just by dissolving the colloidal particles in a suitable medium. Okay. So how do we prepare lyophobic colloids? There are so many techniques to prepare lyophobic colloids, but I will like to discuss only one technique which will help us to understand this electrical double layer. Okay. And this electrical double layer is generally found in metal salts. Okay. So we will take one example of a metal salt to understand electrical double layer. So I hope you have understood what is lyophobic colloid and lyophilic colloid. So lyophilic colloids are those colloids which have attractive interactions between dispersed phase and dispersion medium, and lyophobic colloids are those colloids which do not have attractive interactions between dispersed phase and dispersion medium. Therefore, lyophilic colloids are stable and lyophobic colloids are not stable. It is easy to prepare lyophilic colloids, but it is not easy to prepare lyophobic colloids. So there are so many methods like electrical method and chemical methods to prepare lyophobic colloids, which I am not going to discuss in this class. We will only take one chemical method, that is used to prepare lyophobic colloid of silver iodide salt or silver iodide colloidal solution, and we will use this colloidal solution to understand the concept of electrical double layer. Okay. Okay, now our aim is to prepare silver iodide colloidal solution, right? So let us use one chemical method, that is double decomposition reaction. Now I am taking silver nitrate, AgNO3. I am trying to react it with sodium iodide. And if a double decomposition reaction happens, what will be the product? This cation will go with this anion, and this anion will go with this cation. So that is double decomposition, right? So silver iodide is formed, Agi, and you have sodium nitrate, NaNO3. Now we have successfully formed this silver iodide. Now in your solution, what you have? You have Agi. And we know that Agi is a solid, right? So it will be precipitated at the bottom. So if this is your solution, if this is your reaction mixture, so these are all aqueous solutions, right? Water will be there. Sodium nitrate, this is aqueous, this is also aqueous. So water will be there, and you have silver iodide in this solution, which will settle at the bottom as precipitate. But if you take this sodium iodide in excess quantity, so if you take this electrolyte in excess quantity, what will happen? Now you have, consider this silver iodide colloidal particle. So this is not one molecule, mind you, this is not one molecule of silver iodide, but large number of silver iodide molecules are forming this colloidal particle. Okay. So this is a colloidal particle of silver iodide. Now in the solution, what kind of ions you have? So silver iodide is the bond between silver and iodine is more covalent. So it will not dissociate into ions in water. It will always stay as Agi, but it will not dissociate into Ag plus or I minus. Okay. So silver iodide stays as silver iodide only. But we know that this is NaI, it is a strong electrolyte. When it is present in aqueous solution, it will dissociate into ions. So this is ionic in nature, right? It will dissociate into Na plus and I minus. So in the solution we have Na plus and I minus ions. We also have Na plus and NO3 minus ions, nitrate ions. So we have sodium ions, we have iodide ions and nitrate ions. Do we have anything else? No. We only have silver iodide, sodium ions, iodide ions and nitrate ions. Now what happens? This colloidal particle, it absorbs the common ion. So in silver iodide you have iodine, and even in the solution you have iodide ion. So this colloidal particle will absorb this common ion on its surface. So now this colloidal particle is absorbed by I minus ion on its surface. So what charge this colloidal particle gets? It will get negative charge, right? Now this colloidal particle becomes charged, right? And this is one colloidal particle of silver iodide. Likewise, all the particles of silver iodide absorb this I minus ion, because we have taken sodium iodide in excess. They absorb this iodide ion, and all the colloidal particles acquire negative charge. Okay, when all of them acquire negative charge, what will happen? They will repel each other, and when they repel each other, they will go into the solution. They cannot stay together when they have like charge. Okay, all of the colloidal particles have negative charge, then it becomes impossible for them to stay together. So since they have like charge, that is negative, they repel each other and they diffuse into this colloidal solution. So this addition of this electrolyte makes this metal salts stable by absorbing a common ion from the electrolyte. Okay. So this is how the sodium iodide makes this colloidal solution of silver iodide stable. Now we will see what is an electrical double layer. When silver iodide is present in such electrolyte or in such aqueous solution where you have ions, where you have other ions, then silver iodide particles, they form electrical double layer around them. Now let us see how the electrical double layer is formed. Okay. Okay. Now let us consider one colloidal particle of silver iodide. Till now we have seen that, so these are not different silver iodide colloidal particles. This is one particle in which many silver iodide molecules are present. Okay. So this is the surface of one colloidal particle of silver iodide, and we have seen that this silver iodide had absorbed this iodide ion from the solution. Okay, we saw there are three ions: sodium plus, I minus and NO3 minus. So among these three ions, it had absorbed this iodide ion on its surface. So the colloidal particle now has a negative charge. Now when this colloidal particle has negative charge, what is the second thing that it will do? It will attract the positive ions from the solution, right? So what are the positive ions present in the solution? You have Na plus ions. So from the solution, what will happen? Na plus ions, they come closer to this colloidal particle surface. Okay. Let me use another color. Okay, I will use blue for Na plus. Okay. So this surface had absorbed I minus ions. As a result, the colloidal particle has acquired negative charge. Since it is negatively charged, it is attracting all the positively charged ions, that is sodium ions, around it. Okay. And we know that between negative and positive charge, there exerts electrostatic forces of attraction, right? So since this negatively charged colloidal particle attracts the sodium ions, the diffusivity or movement of this sodium ion decreases, since they are strongly held by attractive forces from the colloidal particle, right? These sodium ions are not free to move in the solution because they are bound by the attractive forces, okay? So there is a layer of positively charged ions around the surface of the colloidal particle, and this layer is called Stern layer, okay? Stern layer, and this layer is fixed. Because, why is it fixed? Because sodium ions are strongly attracted by these iodide ions and their movement is restricted, right? Since they are attracted on this side, they are not free to move into the solution. So this is the Stern layer. The layer of this counter ions is the Stern layer, and this layer is fixed as its movement is restricted because of the attractive interactions. Now one more thing you need to notice here is that each iodide ion on the surface of this colloidal particle is not neutralized by one sodium ions. Randomly few sodium ions come from the solution and they just form a layer on the surface of this colloidal particle, right? But all the minus negative charge is not neutralized by the positive charge. Still this colloidal particle has a net negative charge because all the negative charge is not satisfied by this sodium ions. So this particle will have net negative charge. So since this has some more negative charge, what will happen? There will be some more sodium ions, right? Because we have taken sodium iodide in excess. So there will be another layer in which you have more number of sodium ions. There will also be negative ions, which is nitrate. But the concentration of negative ions is less here because this colloidal particle has a net negative charge because it is not completely neutralized by the Stern layer or the counter ions present in the Stern layer. So it will have a net negative charge. As a result, it will attract some more positive ions from the solution. Okay. So, till certain extent, there will be more number of positive ions and less number of negative, that is nitrate ions. And as you move away from the surface of this colloidal particle, the concentration of positive ion decreases. Okay, the concentration of sodium ion decreases. But to certain extent, the concentration of sodium ion is more than the concentration of nitrate ion because colloidal particle is negatively charged. It is attracting more sodium ions from the solution. Now this layer in which the concentration of sodium ions is greater than the negative ions, this layer is called diffuse layer. Diffuse layer, and this layer also has the name Gouy-Chapman layer. Gouy-Chapman layer. Let me check if the video is being recorded or not. Okay, everything is working fine. Okay. Where were we? Okay, there will be some more positive ions attracted from the solution since all the charge on this colloidal particle is not being neutralized. Okay, this layer is called Gouy-Chapman layer and diffuse layer. But unlike the sodium ions in this Stern layer, in Stern layer the sodium ions are fixed. Their movement is restricted because they are strongly attracted by the negative charge on the colloidal particle. But the sodium ions in diffuse layer are not as strongly attracted by the colloidal particle as the sodium ions in the Stern layer because you have moved away from the surface of the colloidal particle. And we know from Coulomb's law, force of attraction or repulsion is equal to Q1 Q2 by, is it 4 pi epsilon naught R? Yeah, I think this is the Coulomb's law. So the force of electrostatic force of attraction or repulsion is given by this formula, and we see that this force is inversely proportional to the distance. So as you move away from the charged particle, the force of attraction or repulsion decreases. So now this diffuse layer is far from the colloidal particle than the Stern layer, right? Therefore, the attractive force of this negative charge on the sodium ions is less in the diffuse layer or Gouy-Chapman layer when compared to the Stern layer. So the positive ions or the counter ions, so these positive ions are also called counter ions, right? So these counter ions are more free to move when compared to the Stern layer. Therefore, it is called diffuse layer. So their motion or diffusion is not as restricted as the counter ions in the Stern layer. Okay. And as you move far away from this colloidal particle, after certain distance, what will happen? The number of positive ions will be equal to the number of negative ions. Okay. So as you move away from the colloidal particle, the concentration of counter ions decreases. Counter ions here are sodium plus ions. Okay, the concentration of counter ion decreases because the attractive interaction will decrease because distance is increasing. We have seen force of attraction will decrease because distance is increasing. So as you move far away, at certain distance, the positively charged ions and negatively charged ions become equal. That is the bulk solution. So bulk solution starts. Okay. So now this layer combines Stern layer and Gouy-Chapman layer are together called electrical double layer. So these layers are together called electrical, so EDL, electrical double layer. So let me repeat what is electrical double layer. So we have silver iodide colloidal particles, and the silver iodide colloidal particles had absorbed a common ion, that is iodide ion, from the colloidal solution, and this colloidal particle has acquired a negative charge. So when the colloidal particle acquires a negative charge, what will it do? It will attract the positive ions from the solutions. What are the positive ions present in the solution? Sodium ions. So what will it do? It will attract sodium ion near to its surface. So there will be a layer of the sodium ions near the surface of colloidal particles, and that layer is called Stern layer. And this layer is fixed because the motion of the sodium ions is restricted because of the attractive interactions by the negatively charged colloidal particle. Okay. But we see that these sodium ions are not completely neutralizing the negative charge of the colloidal particle. So what will it do? It will still attract some more sodium ions in the solution towards itself. But this layer in which the sodium concentration of sodium ions is greater than the concentration of nitrate ions or negative ions, or I can put it this way, the layer in which concentration of sodium ions is positive ions is greater than the concentration of negative ions, this layer is called diffuse layer. In diffuse layer, the sodium atoms are not very strongly held by the electrostatic forces of attraction because the distance is increasing. Therefore, this layer, the sodium ions are free to move in this layer, and therefore it is called diffuse layer. And this layer also has one more name, that is Gouy-Chapman layer. But when you move farther from the surface, you will reach a stage where the concentration of positively charged ions and negatively charged ions become equal, and that state is the bulk solution in which there is electron neutrality. So there will be no charge. There will be electron neutrality in the bulk solution. So the combination of the Stern layer and diffuse layer around the colloidal particle is called electrical double layer. Now we will see why is this electrical double layer important for colloidal solutions. But before that, we need to understand one thing, that is zeta potential. Okay. So what is zeta potential in electrical double layer? Now you see that here you have a negative charge, okay, more number of negative ions. So this portion is negatively charged, and as you move towards the right or away from the surface of colloidal particle, here there will be no charge, right, because you have attained electrical neutrality. So there will be no charge here. So till here you have a net negative charge. Here some sodium ions are neutralizing iodide ions, but even then there is no complete electrical neutrality. There will be net negative charge here, okay, since each iodide is not neutralized by one sodium atom, okay. There are randomly few sodium atoms are coming and occupying this position, but it is not guaranteed that all the negative charge on the colloidal particle is being neutralized, okay. So there will be net negative charge even including the stone layer, and as you move away from the colloidal particle, the charge will become zero in the bulk solution, right? So there is a difference of charge here. Here there is negative charge and here there is no charge. That means less negative charge. I'll give you an example. Suppose I have a rod. Here I have 10 electrons and on this side I have 2 electrons. Then automatically the electrons will start, a potential difference is created first because there is charge difference. So there are 10 electrons here, that means it is more negative, and there are 2 electrons here, that means this is less negative. So less negative means positive, right? When compared to this side is more positive. So there will be a potential difference created when there is separation of charges, okay? So here you have net negative charge including the colloidal particle and stone layer, and as you move towards the right in the bulk solution, you will have zero charge, no charge, right? So this is more positive, this side is more negative. So when there is a difference of charge, there will be potential generated, okay? And this potential difference between the stone layer and the end of the diffuse layer, okay, is called zeta potential. Okay. So this zeta potential determines the stability of your colloidal solutions. Let us see how. So if you have higher zeta potential, that means if there is large difference between the, so higher zeta potential means, okay, I'll write it here. Higher zeta potential, what does it mean? Higher zeta potential means more separation of charge. So this side will be more negative and this bulk solution will be very less negative. Therefore, zeta will increase. So when this happens, that means your colloidal particle or surface of colloidal particle is more negatively charged, right? When it is more negatively charged, only then zeta potential will be more. So when it is more negatively charged, what happens? There are other particles also, right? This is one colloidal particle. Similarly, there will be another colloid particle in the solution and that will have its own electrical double layer. It will also have more zeta potential. So more zeta potential means the colloidal particle is more negatively charged. If it is more negatively charged, if the magnitude of charge on colloidal particle is high, two colloidal particles cannot approach each other, right? When they try to approach each other, there will be repulsive interactions, right? Because this is also negatively charged. Other colloidal particle, it also has more negative charge because the zeta potential is high. So there will be more repulsions, and these repulsions stop or hinder the colloidal particles from coming together and aggregating. So this zeta potential is keeping the colloidal solution stable because it is constantly repelling the colloidal particles from each other. Okay. So higher the zeta potential, higher will be the charge on the colloidal particle, higher will be the negative charge. If the charge is high on one particle, automatically the charge on the other colloidal particle will be high. Therefore, there will be more repulsive interactions. When there are repulsive interactions, that means the colloidal solution will be stabilized. Okay. So this is how electrical double layer is important for the stability of the colloidal solutions. Now let us see the factors on which the electrical double layer depends. Okay. So I hope you have understood what is zeta potential. It is the potential difference between the Stern layer and the end of the Gouy-Chapman layer. Okay. So the difference of potential between Stern layer and Gouy-Chapman layer is zeta potential. So from here, okay, let me write from here till here. So this is zeta potential, and it is very important to determine the stability of the colloids. Now we will see what are the factors that affect this electrical double layer. The first factor is the ionic strength of the solution. And the second factor is the pH of the solution. And the third factor is the type of counter ion. Type of counter ion. Okay, so we all know what is ionic strength, right? Ionic strength of any solution is given by this formula, CiZi square, where Ci is the concentration of ions in the solution and Zi is the charge on the ions. Charge on ions. So if the concentration of ions in the solution is high, its ionic strength will be high, and if the charge on the ions is high, the ionic strength will be high. But how this ionic strength affects this electrical double layer? So see, if ionic strength is high, that means if the concentration of ions is high, what will happen? There will be more number of counter ions. In our case, the electrolyte was NaI. So if the concentration of NaI is high, there will be more number of sodium plus ions in the solution, right? If there are more number of sodium plus ions, so more number of sodium plus ions will come to form this Stern layer. So this negatively charged surface of colloidal particle will be more neutralized, right? The negative charge on the colloidal particle decreases if large number of sodium ions come and accumulate near the surface, right? I hope you are understanding. If large number of ions come and accumulate near negative charge will be neutralized, right? So there will be less negative charge on the colloidal particle. When there will be less negative charge, it will attract only few ions, counter ions from the solution. Therefore, the length of this diffuse layer will also decrease because only few sodium ions are required, because already the charge is lessened by the sodium ions present in Stern layer. So the width of the diffuse layer decreases. If the width of diffuse layer decreases, the zeta potential will also decrease, right? Because there will be less separation of charge between this layer and the bulk solution. So the zeta potential will decrease. So if the zeta potential will decrease, the repulsive interactions between two colloidal particles will decrease, right? So when the repulsive interactions will decrease, the attractive interactions will increase. So there are two types of interactions. When there are two particles, when there are two colloidal particles with like charge, in this case the charge is negative, there will be electrostatic repulsions and there will be van der Waals attractions. Okay. So now, because ionic strength has increased and the counter ion has neutralized the negative charge on the colloidal particle, and because of that the length of the diffuse layer is decreased. If the length of diffuse layer decreases, the zeta potential decreases. The When the zeta potential decreases, the repulsive interactions will decrease. So when the repulsive interactions and electrostatic repulsions decrease, van der Waals interactions dominate. So there should be a balance between, for a colloid to be stable, the repulsions should be greater than van der Waals attractions. Please pardon me for my handwriting. So the repulsion should be greater than van der Waals attraction for the colloidal solution to be stable. But since we have used high ionic strength, there will be more number of counter ions that will neutralize the negative charge on the colloidal surface. As a result, the zeta potential will decrease. When the zeta potential decreases, electrostatic repulsion will decrease. When electrostatic repulsion decreases, the two colloidal particles can come closer to each other. When they come closer, they start precipitating. So, if you use an electrolyte of high ionic strength, that will destabilize your colloidal solution. Okay. Now, how does pH affect this electrical double layer and stability of colloid? So, you might have heard of a pH which is called isoelectric point. Isoelectric point or isoelectric pH. So at this pH, what will happen? All the charge on the surface of colloidal particle will be neutralized. There will be no charge. The charge becomes zero. What happens if the charge becomes zero? There will be no electrical double layer. So when there will be no electrical double layer, there will be no electrostatic repulsions. The kind of forces that exist are only van der Waals attractions. So when there are only van der Waals attractions, so the charge is zero, there is only van der Waals attractions, the colloidal particles come closer to each other and they coagulate or precipitate. So this thing will destabilize the colloidal solutions. So the pH should be far away from the isoelectric pH. Okay. So for any colloidal solution to be stable, the ionic strength should be low. Low ionic strength is preferable. The pH should be such that it is far away from the isoelectric pH. Okay. So type of counter ions. So how does this electrical double layer depends on the potential of electrical double layer depends on type of counter ions. Now see here, the electrolyte we had was sodium iodide, and the sodium ion is monovalent ion. It has only one positive charge on it. But instead of sodium iodide, if you took some calcium chloride, calcium is a divalent cation. So this will be more capable of neutralizing the negative charge on the surface of this colloidal particle. So when this is surrounded by calcium ions, more negative charge on the colloidal particle will be neutralized. So as a result, there will be less number of counter ions attracted towards the surface. So this diffuse layer length or the distance of diffuse layer, width of diffuse layer will decrease. As a result, zeta potential will decrease. What happens when zeta potential decreases? When zeta potential decreases, van der Waals interactions dominate over electrostatic interactions, and therefore the two particles come closer to each other and they can coagulate or precipitate. So there should be less charge on the counter ion. So divalent cations are not preferable. You can prefer monovalent cations for stability of colloidal solutions. So if you want the colloidal solutions to be stable, you have to maintain this electrical double layer, and this electrical double layer depends upon three things or three factors: ionic strength, pH and type of counter ions. So when the ionic strength is low, if the ionic strength is low, the zeta potential will be higher and your colloid will be stabilized. If the pH is far away from the isoelectric point, the charge on the particle will not be neutralized. Therefore, the pH which is far away from isoelectric point is preferred, and monovalent cations are preferred over divalent cations, or monovalent anions are preferred over divalent anions. That means the counter ion should have less charge. Okay. So I hope you have understood this concept of electrical double layer. It is a bit complicated. It's not actually complicated, it's simple. But I think I have made it complicated. If you have any doubt, you can ask me in the comment section. And if you want me to redo this portion in small bits or parts, I'm ready to do that. Please comment in the comment section. Okay. I hope you have understood. If you have not, please let me know. Okay. Thank you so much. See you in the next class.